Welcome to the recording on section 6.4. In part A, we will talk about derivatives of logarithmic functions. First, we will use the fact that the derivative of e to the x is itself and use implicit differentiation to compute the derivative of the natural log of x. This is a technique that we will use often in this class. First, I write down y equals the function that we are interested in differentiating. And then I want to cancel out this part so that this is simpler. So I take e to the y and e to the right-hand side as well. So because e to the x and natural log of x are inverse functions, this right-hand side is equal to x. So I have this quantity, which I will use later. So I label this with the blue star. Now I will differentiate with respect to x. So I have d dx of the left-hand side and d dx of x. d dx of x is 1. And on the left-hand side, this is an important step. So the derivative of e to the y with respect to y is just e to the y. But because of chain rule, I have to multiply this with dy dx. But what we're interested in finding is dy dx because y is the natural log of x. So then I multiply both sides by 1 over e to the y. So I get that dy dx is equal to 1 over e to the y. But because of this quantity, we know e to the y is equal to x. So I have 1 over x. And so the derivative of the natural log of x is 1 over x. So this one is something that you should memorize because we will use it often. Last time, we learned that the derivative of b to the x, if b is a positive number, is equal to b to the x times the natural log of b. We can use this fact in implicit differentiation to compute the derivative of log b of x. We will do actually the same steps as in the previous slide. First, I write down y equals to the function I'm interested in differentiating. And I want to make the right-hand side be simpler. So I will apply the inverse function of log base b of x. And that would be b to the x. So I take b to the y on the left and b to the log base b of x. So because b to the x and log base b of x are inverse functions, the right-hand side is equal to x. And I have this equality, which I will use later. So I'm labeling this with double star. Next, I differentiate with respect to x. So I take d dx of the left-hand side and d dx of the right-hand side. The right-hand side is equal to 1. And now I have to apply chain rule. So first, I compute the derivative of y. Sorry, I compute the derivative of b to the y with respect to y. And according to the green star, this is equal to b to the y times the natural log of b. And I have to multiply this with dy dx because of chain rule. Now let's replace b to the y with x, which we know is true because of this quantity here. So I replace b to the y with x, and I write down everything else the same as before. Next, I multiply both sides by 1 over x times natural log of b. And this is the derivative of log base b of x. This one we don't use as often, so you don't have to memorize it, but when it does come up, you'll have to go through this same process. Knowing that the derivative of natural log is equal to 1 over x, we can use that to compute the derivative functions that look like natural log of some function of x. So first, let's review a few things. First, I want to talk about the derivative of sine x and cosine x. The way I remember these is to write down these 4 values. So I write down sine x, cosine x, negative sine x, and negative cosine x, and repeat the same thing. And when I go down, this means that the derivative of what's above is equal to what's below. So the derivative of sine of x is cosine x, and the derivative of cosine x is negative sine x. And I can keep going that way. If I go up, that will be when you are computing integrals. And if you forget where the minus sign should go, one thing you could do is to sketch the graphs. So this is a sketch of sine x. And we see that between negative pi over 2 and pi over 2, sine of x is increasing, so the derivative is positive. And if we compare that with the graph of cosine of x, between negative pi over 2 and pi over 2, cosine of x is positive. So it makes sense that the sign here should be positive instead of negative. We also want to review that another way to write tangent of x is to write it as sine of x and cosine x. And cotangent of x is equal to cosine of x and divided by sine of x. So please take a minute to attempt this on your own. So we have the natural log of sine of x, and we want to compute its derivative. Welcome back. To compute this, we can apply equation 1 and also chain rule. So first, I do 1 over what's inside of the natural log, so that is sine x. And then I take the derivative of what's inside, so sine of x. So again, I write 1 over sine of x, and I multiply that with this value, which we said was cosine of x. And you can simplify this further. So cosine x over sine of x is cotangent of x. In the next slide, we will use equation 1 to help us compute some integrals. Now, instead of working with the natural log of x, we're working with this function, natural log of the absolute value of x. This means that we can input negative numbers. So the domain of this function are all numbers except 0. So the graph of this function can be drawn over here. So in blue, this means that when x is positive, then f of x is equal to the natural log of x. When x is negative, f of x is equal to the natural log of negative x. So using what we learned, we know that the derivative of natural log of x is 1 over x. So f prime of x is equal to 1 over x when x is positive. And we can use chain rule for the situation where x is negative. So the derivative is 1 over negative x, and you multiply this with the derivative of what's inside, so negative 1. And this is the same as 1 over x. So f prime is equal to 1 over x for all x in the domain of f. Now let's look at the picture on the right. These are the points that are in y equals 1 over x. So in red is the graph for the derivative of f. Now, when x is small and positive, so around here, the graph for f of x is very steep and it's increasing. So it has positive slope, and so f prime for those x would be big and positive. When the value of x is small and negative, so around here, the graph is also very steep, but it's decreasing. So it has negative slope. And so the absolute value of the derivative is big, and the actual derivative is negative. Now, this allows us to take the integral of 1 over x, and that would be the natural log of the absolute value of x plus the constant. So the absolute value is necessary because the natural log is only defined when this value is positive. Now let's use what we just learned to compute a different integral. Here I want to calculate the integral of cotangent. And I know that cotangent is cosine of x over sine of x. So this is nicer to work with because I know the derivatives for cosine and sine. In this class, we will learn many different techniques for solving integrals, but in Calculus 1, you have only learned a few, and one of them is u substitution. So let's try that. So let's try maybe u can be cosine x, u may be sine of x, u may be 1 over sine of x, and there might be more, but let's try these first. So du, then if u is cosine of x, would be negative sine x dx. So this is not very promising because then I'll have, I can't really use these to do u substitution. But let's try when u is sine of x, then du would be cosine x dx. So if I try to do u substitution here, I will have 1 over u, and then I'll have du because I can replace cosine x dx with du. So that looks good. So let's use this one. So from this equation, I have that this integral is the natural log of the absolute value of u plus a constant. Now I need to replace u with sine of x because this is the substitution we were using, plus a constant. Now let's practice using these two equations to solve different problems. This is similar to one of your web work problems. So far, you have only learned u substitution, so let's try to apply that. Let's try, maybe u could be natural log of x, u could be maybe 1 over x, and maybe u can be 1 over natural log of x. So there are different things you can try here. So for the first one, du would be 1 over x dx. And actually that one looks good because then I replace 1 over natural log with u. So 1 over natural log of x is u. So then the squared would be u squared. So then I have, oh, sorry. So then this would be 1 over u squared. So then I have 1 over u squared. And then I can replace 1x dx with du. So this is du. And this is now something that I know how to solve. So first, let's rewrite this as u to the negative 2 du. So the integral would be u to the negative 2 plus 1. And I divide this with the exponent. So I divide this with negative 1. So plus a constant. So I get negative 1 over u plus the constant. And now I just have to replace u with natural log of x. Next, let me go over how to solve this problem. First, let me rewrite this function as the natural log of x to the 1/5. We see that this 1/5 is inside of the parentheses. So this is the same as 1 over 5 times natural log of x. And now this just becomes 1 over 5 times the derivative of natural log of x, which we just learned is 1 over x. This is part B of the recording. I want to explain how to do a technique called logarithmic differentiation. It might be new to you. This is a technique that is useful when you are trying to differentiate something that is normally hard to differentiate, but once you apply the natural log function, it becomes much easier. This is something that we will use often in this class. So I want to differentiate this function. So I let this function that I want to differentiate be equal to y, and then I take the natural log on both sides. Now here, I want to simplify this a little bit. I know that I can apply this logarithm rule where if the exponent is inside of the parentheses, I can bring this down. So in this situation, the exponent is ln x, so I can bring it down. So let me do that. Ln x times natural log of 4 plus 2x squared. And now this is good because I know how to differentiate this. So this is something where I can use the product rule. So first I take the derivative of the first part and multiply that with the second part plus the first part and then the derivative of the second part. So that's the product rule. And then I'm also applying the derivative of the left-hand side. So I'm applying chain rule. I know that the derivative of natural log of y with respect to y is 1 over y. This is by equation 1, the one we've been talking about. And because of chain rule, I have to multiply with dy dx. And before I move on with the left-hand side, let me continue with the right-hand side. So the derivative of ln x is 1 over x. And the derivative of this quantity, we have to use chain rule. So I have 1 over what's inside of the natural log times the derivative of what's inside. So I have 0 plus 4x. And now I will multiply both sides by y. So I have y times this whole thing. So that whole thing is 1 over x times the natural log of 4 plus 2x squared plus the natural log of x times 4x divided by 4 plus 2x squared. And finally, I just have to replace this y with the function. So I replace y with the function 4 plus 2x squared to the natural log of x. And then over here, I copy down what I have here. And this is my derivative. And again, the key step is where at the very first step, you apply natural log to both sides, and then you apply implicit differentiation. Now, please practice applying logarithmic differentiation using this function. And you can see the solution in the textbook, example 16.